Good morning. Yes, I am here, running late today. Seems like Monday at my house. What about you? Do what? Ooh. Yeah, my whole family was running behind today. I don't know what the deal was. I think it's all that holiday, the holiday time we had yesterday and the long weekend, and so those are always the excuses anyway. Let me get set up here just a moment and we'll get back into some trigonometry, okay? All right, are y'all awake out there this morning? Everybody awake? Yeah, that's great. Good. Okay. So last week we'd just kind of gotten a start on everything. Started talking about the class, the syllabus, and then went into section 6.1 and a little bit in 6.2. I do not have with me exactly what I assigned you last week. I just happened to have my textbook at home with me, so I had to walk from my car to here this morning. I was running that late. That's not normally how it goes, but it was just fortunate, I guess, that I had my textbook there with me. I know that we were working, though, in section 6.1 and 6.2 a little for today, doing some practice problems having to do with some angles and going from degrees to radians, radians to degrees, working with the two formulas that we worked with last week, the arc length formula and the area of a sector of a circle. And then we had also started talking about the unit circle. Okay, we'd started talking about the unit circle a little bit as far as, the measures around it in degrees and radians, those angle measures, as well as I believe we started looking at the ratios of the trig functions. We might have just barely gotten into that, I think. So let's see where we were there. Let me go back first to section 6.1, and I asked you all to practice with some problems. So if you have a question about some of those you were practicing with, let's look at a few just to kind of get back on track with that today. Okay, does anybody have a question there? All right, let me give you, go ahead. Yes, and please use your button, please remember. Thank you.
On 81 through, let's say 81 through 84.
Okay, so down on page 360 is where we're looking?
Yes, ma'am.
In that first section? Alrighty.
It may be just a simple me plugging it in wrong. For the area, I know it's area measured in squared. The units are measured squared. But when you plug it in, do you square the area as well, or is it just?
It's just the r that gets squared. Okay, so it's 1/2 r squared theta. Let's go through one though, just to make sure we're all seeing what's going on with those. So let's. I wrote down 81 just for that number came to mind when you said that, but let's look at and see what we've got on 81. It says theta is going to be 1/3 of a radian. The area is 2 square feet. The radius, we don't know what that is. Okay. We're using the formula area equals 1/2 r squared theta. And we did say, A here is standing for the area of a sector of a circle. R is the radius, and theta is that central angle measure. So that what we're actually looking at, if we were to draw a picture up here, we'd have our circle, our center. We have some angle marked off. We're calling that angle theta. This is the radius. What we're looking for, though, is the area of this sector here. Okay, so that little piece of pie, that's what we're looking for. All right, so in this particular problem, though, we know that the area is equal to 2 square feet, so we're going to replace A with 2 equals 1/2. The radius is what we don't know, so we've got R squared. Theta is already in radians. Remember, that was a requirement for this formula. The angle measure must be in radians. So theta is 1/3. Okay, so we can just write it like that. So in this problem, we're looking for R. That's what we're trying to solve for. We'll have 2 equals 1/6 R squared. I'm just multiplying the 1/2 times the 1/3 due to the commutative property. Remember the commutative property that goes with addition and multiplication. It says you can multiply or add in any order. It does not matter. Okay, so we're multiplying 1/2 times 1/3. Now to get R squared by itself, I'll need to, instead of, I've got that 1/6 there, so I'll have to divide by 1/6, but that's actually the same as multiplying by 6. So I'm going to put down that I'm going to multiply both sides by 6. 1/6 times 6, those cancel and just leave us with 1. Okay, so that I get R squared over there is equal to 12. But I don't want to know what R squared is. I need to know what R is equal to. So I'll have to take the square root of both sides. Square root of 12 then is equal to R, because the square root of R squared is R. But the square root of 12 can be simplified. Square root of 12 is equal to the square root of 4 times 3. Remember, when you're simplifying radicals, you're looking for a perfect square factor that can divide into that. Okay, so we want that perfect square factor of 4. The square root of 4 there is 2, and then we still have the square root of 3. So that's what we're looking for the radius. And the radius here then would be in which units? Feet, right. So it's 2 square roots of 3 feet is what we're looking at there when we get that. Does anybody have a question on that one? Look at that just a moment. See if you have a question there. Does that make sense how we plugged in, did the substitutions? Okay, let me start this around. I don't think we have one at the back, so let me start that around and let y'all sign in on that. Okay, anything else from that part there that you wanted to ask about? Does that kind of help clear up that portion? Go ahead.
Can you go over 83 too?
83, okay. So R is 5 miles. A is 3 square miles. And this time we're looking for theta. Now, even though when we're given theta in these problems, we have to make sure that theta is in radian measure in order for the formula to work. But if we're looking for theta, then it's going to come out to us in radian measure. It's going to come out in the right units, okay? So we don't have to do any adjustments if we're looking for that part. A equals 1/2 R squared theta is the formula. We have 3 equals 1/2 5 squared theta. That's what we would have there. So 3 is equal to 1/2 times 25 times theta, because 5 squared is 25, right? Okay. Are we all okay so far together? That means then 3 equals 25 halves theta. To get rid of my 25 halves, I'll multiply by the reciprocal 2 25ths. So 2 25ths times 3 will be 6 25ths equals theta, because all that stuff over there canceled. So 6 25ths equals theta. Now, I know we're practicing working on these without a calculator. We didn't use a calculator just then on this problem. The book probably did not leave the answer 6 25ths. They're probably going to leave it in some decimal form. If you wanted to change this one to a decimal form, it's not too bad, because what would we need to do?
You just divide the 6 divided by 25.
You can do 6 divided by 25, right? So here's one thing you can do if you want that decimal. 6 divided by 25, you'll have to add some decimal places out here, right? That's one way. Another way, 6/25, that denominator being 25 is helpful. 25 goes into 100, right? So we can see how many hundredths it is, giving us that decimal that we're looking for if we want the decimal. So that would be times 4 to get there. This one times 4 is 24. So that's 0.24, right? If you want to change it to that. I'm fine with this right here, 6/25, okay? 6/25 radians is what we've got there. Now your fraction should be in lowest terms. 6/25 is in lowest terms, okay? There's no common factors, in other words.
So we just use that formula.
Right, you just use the formula, A equals 1/2 r squared theta for all of those where you're finding the area of the sector. Okay? And plug in what you know and solve for what you don't know. That's pretty much what we're doing in that part. That's correct. Anything else from that first section? Yes?
Could you go over 89?
89. Let's go down to that one. And that one on 89, we want to find the arc length and the area, both. So we're going to go into a little bit different formula as well there. 89, we have a picture, which I will attempt to draw. We have 70 degrees. We have 12 yards. Here's S, here's A. Okay. So we're going to use this formula and this formula. Okay. Doesn't really matter which one you start with. In both cases, we have the radius and we have theta, and we're looking for the other part. So if I want to go ahead with area equals 1/2, 12 is the radius, so 12 squared, and theta is 70 degrees. Well, that's a little bit of an issue. 70 degrees equals how many radians? We will need to know that. 70 degrees times, what do we multiply by to get radians? Pi over 180. Well, what's that going to give me? 7 pi over 18, right? 7 pi over 18, because 10 goes into 70, 10 goes into 180. So we're now getting 7 pi over 18 radians. So 7 pi over 18 radians is the same then as 70 degrees, is what we're saying there. So we'll have, what would we need to do next here? The 12 squared, right? What's 12 squared? 144. Now it looks like I'm going to need to do some reducing or canceling, however you want to say there. I know 2 divides into 144. Does 18 divide into 144? Let's just do 2 into it, and then you can see. 2 into 144 goes 72 times. 18 divides into 72, right? 18 goes into itself once, into 72, how many times? 4. So what's that leaving me with? 4 times 7 pi, so that's 28 pi square yards for the area. Well, I put it up there. I should have put it here. Here we go. Questions on that calculation there? Anybody have a question on that part? So we did 2 cancellations. We divided the 2 into the 144, and then the 18 into what was left over after we divided the 2 into the 144, right? The 18 into the 72. For the other calculation, S equals r theta, we're going to say S equals 12 times, remember our theta value was 7 pi over 18. Now we know that 6 divides into 12 and 18. Remember, this is 12 over 1, just to clarify. That's 12 over 1. So 6 divides into 12 2 times, 6 into 18 3 times. So we have 14 pi over 3. 14 pi over 3. This is the arc length we're talking about here. So what units is the arc length going to be in here? Yards, right. So 14 pi thirds yards. Now, like I was saying the other day, or I think I mentioned in here at least, if you want to check these against your book where they have them in decimal terms, you all, can still punch that in your calculator and check that out and say, 14 times pi divided by 3 equals, and make sure it's lining up with what you're seeing in your textbook when you're working through this on your own. These answers here is what I'll be looking for, though, when we take our test, okay, since we won't be using the calculator. Hopefully none of the computations so far have been too intense as far as that goes. All right, let's move over into section 2. I gave you a little bit of an assignment in section 2, right? Yeah. Did I? Yeah, okay. I'm thinking I did. So let's look and see what we have there, because we had started talking about more how these things fit on the circle. We looked at getting those coordinates, that square root of 2 over 2, square root of 2 over 2. I believe we did that last Thursday, right? On the unit circle. So let's look here in section 2. This was over on page 375, I think is where we were looking. Maybe some on 376, I don't know. All right, where do you have a question there? Does anybody have a question on that part? Yes, go ahead. The whole second part. Which part? Okay, 31 through 37. And that's the part I thought might give you a little bit of trouble, because we had just kind of started, and I thought, well, let's see how far we can get with that, and we'll look at it then. Okay, let me just, as a reminder, go back through a little bit of what we talked about last Thursday. Okay, we were focusing on that unit circle where we said the radius is equal to 1 on the unit circle, right? Radius is equal to 1, so we knew about that. We knew that when we were working with the unit circle, before I put that part up, when we were working with the unit circle, we knew that we had the circle. We're on an XY axis here. We knew that when we got these coordinates out here, we talked about how they related to sines and cosines. How did they relate? The cosine of an angle is always going to equal x over r, and the sine of an angle is going to be y over r. Okay, so in a unit circle, since r is equal to 1, so that means that the cosine of the angle will be just the x coordinate, and the sine will be just the y coordinate, since it will be x over 1, y over 1. We wrote this up last class, right? Okay, I want to make sure. Okay, some of you are looking at me, making me wonder here. So I want to be certain. We did put up x over r, y over r, and I'm not sure if we got to the other trig functions or not, but we're going to put those back up here anyway. Tangent. Remember, the trigonometry is showing a ratio of sides. Here is what we're looking at, ratios of sides in triangles. The tangent ratio is y over x. And then the other 3 trig functions will be reciprocals of these 3. Okay, so we would have cotangent is equal to The reciprocal of the tangent, I'm going to first write because that's how it's going to help me remember. The reciprocal of the tangent is the cotangent. When I write 1 over something, that means I'm reciprocating. I'm flipping it. Instead of just tangent of, well, let me change that to theta there because I use tangent theta up here. So 1 over tangent theta, okay, which is going to be x over y. The secant will be the reciprocal of the cosine, and the reciprocal of the cosine will be r over x, and the cosecant will be the reciprocal of the sine, be r over y. Okay, these are listed in your book over on page 374, if you want to put that for our reference there. That's where those are listed. So while I have this up here, before we go into those actual problems on the page, let's look at the trig function values. I don't think we went through a whole angle yet, so let's do that. Let's look at the trig function values for the 90-degree angle, okay? And we'll use 90 degrees here, so just to keep it maybe more easy for you to think about in that sense. So 90 degrees. The cosine of 90 degrees will be equal to what? Yeah, because we're looking at these coordinates here where when we draw out that 90-degree angle, whoops, kind of made an extra mark in there. When we draw out that 90-degree angle like that, we're looking at the coordinates that correspond to where that terminal side hits on that unit circle. Go ahead.
That'd be 0 over 1 way.
Right, so 0 over 1, whoops, I can't write with an eraser. 0 over 1 is equal to 0. So note that the cosine is equal to the x-coordinate over the radius value. Our radius value, though, is 1. So our cosine here, in anything to do with the unit circle, the cosine will be equal to the x-coordinate. Whatever your x-coordinate is will be the cosine for that particular angle corresponding to that point. Okay? What does that mean about the sine then? The sine of 90 degrees will be just 1, right? The y-coordinate. I heard somebody over here say it, but the y-coordinate. So what we're saying here is that this part, when we're in a unit circle, and I keep stressing that because we won't always be working with the unit circle. Sometimes we will have a different radius we're dealing with. But in a unit circle, this x-coordinate will be the cosine of theta, and then the y-coordinate will be the sine of theta. Well, you can remember that because they're in alphabetical order, right? X and Y is in alphabetical order, so is cosine and sine. Okay, so the cosine goes with the X, the sine goes with the Y. Just trying to help you connect that there a little bit. See what I'm saying? Okay, cosine will correspond to your X coordinate, the sine will correspond to your Y coordinate for these angles here. Another thing, whenever we write up cosine and sine and what they're equal to, we always put an angle out here. It might be in degrees, it might be in radians, we might be dealing with theta, some unknown angle. But we never just write COS. Some of you do, but let's not do that, okay? Let's just not write COS, because whenever you're dealing with a trig function, you have to have something you're taking that trig function of. We have to know, what it's dealing with. So we have to say something like cosine of 90 degrees, cosine of 30 degrees, okay, or cosine of pi over 6, whatever that angle is. We call that angle out there the argument of the trig function, okay? It's not an argument where we're going to fight back and forth, but an argument of a trig function is whatever it is we're taking that trig function of. So that's a little terminology there for you. If you worked with like logarithms and things like that as well, maybe you took the first part of this class, then you know that they also, you have arguments involved sometimes with logarithms, exponential functions, things like that. So the argument that you're looking at. So we're interested in the trig, though, in here. So now let's move on down to the tangent. The tangent of 90 degrees. So over here, I look over here at my chart for now, because I don't have it in my head yet, right? So I say the tangent is equal to y over x. So I'm looking back at my coordinates up there, 0, 1, the y over the x, 1 over 0. What's that equal to? It's undefined. Why is it undefined? Okay, so, well, technically we just can't divide by 0, can we? We can't divide 1 by 0. So just a little refresher on that. I think you all will remember this easily. But you know, if you have 6 over 3, that's equal to 2. And you can check it because those things multiply and give you back the 6. These have to multiply and give me back 1. It's never going to happen, is it? Multiplying by 0. It's not going to work. So any number, whatever it might be, I'll call it k, over 0 is undefined. 0 over a number, though, you know, these have to multiply and give me back that 0 up there. That's going to be 0. If 0 is on top, the fraction is equal to 0. If 0 is in that denominator, though, it's undefined. So we'll get some undefined trig values here. The cotangent of 90 degrees. It's the reciprocal of the tangent. So I probably want to think back to where I had that 1 over 0. It's 0 over 1, which means it's 0. If one of the values is undefined, then its reciprocal will be 0. And vice versa. If one of the values is 0, its reciprocal will be undefined. The secant of 90 degrees. Secant's going to be, I don't like to think of r over x, but I just like to think about the secant's going to be the reciprocal of the cosine. So I'll look back up at my cosine up there, which was 0, or 0 over 1. When I reciprocate that, what am I going to get? Undefined again. And the cosecant of 90 degrees, the cosecant will be the reciprocal of the sine. So the reciprocal of the sine, I look back at my sine, it was 1. The reciprocal of that is also 1. Okay. And we have our 6 trig function values. What we're focusing on right now is just being able to get what these values are, where they come from, how to get those ratios. So we've just worked on the trig function values for 90 degrees, for a 90-degree angle. Let's try another one here, okay? Let's try the trig function values for the pi over 4 angle. This time I'll put it in radians like that, okay? So we want to do the cosine of pi over 4, sine of pi over 4, tangent, cotangent, secant, and cosecant. Now I think we derived out those coordinates. That's a horrible circle. I think we'll redo that one. I think we worked out the coordinates for the pi over 4 angle. Do you remember those? Pi force is actually 45 degrees. Right, square root of 2 over 2, square root of 2 over 2 are the coordinates there. So let me give you just a minute to write down those first 3 anyway. Okay, so what's the cosine going to be? Square root of 2 over 2, because that was the x coordinate, right? And the sine is going to be same thing, square root of 2 over 2. What about the tangent? 1, because it is y over x. And they're the same. So that would be equal to 1. The x and y coordinates are the same for this one, so therefore the tangent will be equal to 1. The cotangent is the reciprocal of that tangent, so it will be 1 also. The secant is going to be the reciprocal of the cosine. What's that going to be? Okay, square root of 2 I heard, so we are flipping or reciprocating that cosine, 2 over square root of 2, and then you rationalized it, right? That's what happened here. So we get 2 square roots of 2 over plain old 2, but those 2's cancel, and it is just the square root of 2 after having rationalized that denominator. What about the cosecant? It will be the reciprocal of the sine. Well, you only needed to do that work once. Since the sine and the cosine are the same thing, when we reciprocate them, we're going to get the same thing. So that's what we want to use there. Square root of 2 for that one. And while we're on their basic angles here, let's do one more off our unit circle. Let's do 120 degrees. Any questions on the 45-degree angle? Trig functions for it. Go ahead.
On the secant and cosecant, I get what's going on with the math. I don't understand how you're, like, when I write it out, it's 2 over the square, 2 over the square root of 2 over 1.
Okay. Which is what I have right there.
Never mind, I get it now.
Right? Are we good? Okay. No problem. All right. Anything else so far on this pi over 4 angle up here? Anyone else have a question there? Yes, go ahead.
On the square root of 2 over 2, is that something we'll eventually just remember for the angle? Or
Yes.
X and Y?
Yes, that is square root of 2 over 2, square root of 2 over 2. Yes, you will. I don't recall if last time I showed you or not, but I think I might have shown you where I have that unit circle posted on your D2L site. Yeah. Here's what I would advise you to do, okay? This is just my advice. I would advise you to probably print this thing off, you know. It's going to be here. You can use it from here, but it might be handy just to have an actual printed copy of this value when you're working on these problems from the textbook for you to refer to. Now, no, you won't have this on the test. I'm not going to give this to you on the test because after you work with it so much, you're going to remember these things. You're going to know that the coordinates for the 45-degree angle are square root of 2 over 2, square root of 2 over 2. The coordinates for the 30-degree angle are square root of 3 over 2, 1/2. And that the coordinates for the 60-degree angle are 1/2 square root of 3 over 2. You're going to know how those relate in the other quadrants when you go around the coordinate system. Okay? But in the meantime, until we get to that part where you know all that, you might want to use this kind of as a reference or study with this a little bit. Okay? The easiest way to do that's probably going to be to print it off, more than likely. That's just my advice on it. So we were going to look at that angle 120 degrees, right?
Yeah,
120. So I'm drawing a sketch up here. We'll definitely call it a sketch. Now the coordinates at 120 degrees will be Negative 1/2 square root of 3 over 2. Good. And for now, that could be found from that unit circle, or, later you will know that. You will just know it. Okay, I promise it will happen. I think you will just know that. Now, what you will have that you'll be able to use on the first test will be a blank unit circle. And you're saying, blank? Well, how's that going to help me? Well, you're going to fill it in, right? You're going to fill it in. So you want to know these things. You want to be learning these. Once you get that first quadrant, you use it to guide you through the other three. All right, so negative 1/2 square root of 3 over 2. What is the cosine of 120 degrees?
Negative 1/2.
Negative 1/2, that x coordinate, that's right. What's the sine? The y coordinate, square root of 3 over 2. Tangent. Tangent here might be a little bit more work. It's the y over the x. Well, we certainly don't want to leave it looking like that. That's what we call a complex fraction, where we have fractions inside of fractions. We don't want to leave it looking that way. So what we'll do is simplify that. Now, most of you know that if you have, square root of 3 over 2 over that negative 1/2, it means that you're dividing, right? So that's square root of 3 over 2 times the reciprocal. When we divide by a fraction, we multiply by the reciprocal. So just pulling out those old rules. These twos cancel, and we get negative square root of 3. Now, you'll see me up here looking at it like this, though. When I have this square root of 3 over 2 over negative 1/2, I'll do that, and I'll say, oh, that's negative square root of 3. Because that's what ended up happening down here. When I flip that bottom one, if my two denominators are the same in my complex fraction, then they're going to cancel. And I'm just going to be left with those top parts, okay? Square root of 3 over negative 1. So just so you can kind of see what's going on here. What's really happening is we're dividing and then multiplying by the reciprocal. Okay, we're dividing, and by doing that, we're multiplying by the reciprocal. But as long as your denominators are the same up there, you can just cross those out and work with what's left. Okay.
So is cosine the same thing?
Okay, so is the cotangent going to be the same thing? Well, the cotangent's got to be the reciprocal of the tangent. So what's the reciprocal of negative square root of 3? 1 over negative square root of 3, right? Negative square root of 3 is understood to be over 1. Are we together on that?
Yeah.
Negative square root of 3 is negative square root of 3 over 1. We just don't have to write that over 1 part. So when I flip that or reciprocate it, I get 1 over negative square root of 3. Let's rationalize that, though. I'll multiply by what? Square root of 3 over square root of 3, which will give me square root of 3 over negative 3. Well, that just means it's negative square root of 3 over 3. Right? It doesn't really matter if I put my negative in the denominator or out front or up on top. It's still going to be that negative fraction square root of 3 over 3. The secant, we're going to flip the cosine. Negative 2. Y'all like that one. That one was kind of nice after those others. For the cosecant, we'll reciprocate the sine. So we start out, we get 2 over square root of 3. I rationalize that. I'm going to have 2 square roots of 3 over 3 for that one. So we're looking at these things to kind of get a better idea, of how these trig function ratios work. And what we want to do here, though, is see how what we just did with these 3 angles, that's going to help us with 31 to whatever, okay? So that's telling us the key to get into those. Might have seemed a long roundabout explanation, but hopefully it'll help us see those things a little bit better. So we're going to go down to one of those problems now. But I think we needed to see through some of these angles and see what was going on with these. Let's go over then to on that part that was actually asked about originally, like 31. So now we see the directions say find the exact value of the expression. Okay, so we want to find the exact value. That just means we're not using the calculator. We're going to get exact values and not decimal approximations. So sine 45 degrees plus cosine 60 degrees. Again, this would be a helpful place to use that unit circle when you're working through. You see the benefits of having that in front of you to kind of get those things in your head. The more you see it, the more it'll get up here. But we've worked with the sine, or we've worked with the 45 degree angle a while ago. We actually did work with the sine of 45 degrees. What was that?
It's square root of 2 over 2.
It is square root of 2 over 2. Now we did not work this morning, I don't think, with the 60 degree angle. We worked with the 120 degree. But do you have that cosine of 60 degrees? It's 1/2. Okay, so you might want to use the unit circle to help on this. Now to put these values together down here, we notice that they have a common denominator already. When we add fractions with a common denominator, we keep that denominator, and then on top we combine. Problem here is we have a radical term and a non-radical term. So we cannot actually physically combine those. What we do is leave them written like this, square root of 2 plus 1. That's fine to leave for your answer. That's shown that you've added them together, you put them together. The textbook may show it a little different from that. I know at one time the textbook would put something like this. Do you recognize that that's the same thing, though? Do we recognize that those are the same? They pulled out the denominator, essentially, so they pulled out 1/2 and then just left that top part. 1/2 times square root of 2 plus 1 would be the same as square root of 2 plus 1 over 2. Okay. So just in case you see it differently, you want to be able to recognize different forms of the same answer. That's pretty important, too, to be able to do. Let's see. Let's go down and try another one of these just to make sure we're getting this here. How about 40? 40 says 5 cosine 90 degrees minus 8 sine 270 degrees. Let's give it its own page here. So you might think here about where the 90 degree angle is and the 270 degree angle, and you're definitely going to need to think about the coordinates at each of those.
What does it mean when I was like a 5?
Okay, so that's a good question. The question here was, what does that mean when it has like the 5 in front of it, 5 cosine whatever? What does that mean? Means we're going to multiply 5 times the cosine, right? It's just like if we had 5x in an algebraic equation, that would mean 5 times x. So here we have 5 times the cosine of 90 degrees minus 8 times the sine of 270 degrees. That's what we're working with. So the cosine of 90 degrees is 0. So we actually have 5 times 0, right? And then over here, minus 8 times, what's the sine of 270 degrees? Negative 1. So we've got 0 plus 8, giving us 8 for the answer there. It's a good question, though. When there's values out in front of the trig function, that means we're going to multiply. They're just written there in front. There's also some problems in here I don't think we assigned yet, but things like this. It might say the tangent of 6 pi. Let's look at that a minute. Our unit circle only went from 0 to 2 pi. So what we do is we keep wrapping around that angle. We keep wrapping those values around so that we have this. One time around gets us to 2 pi. If I go around again, I'm at 4 pi. If I go another revolution, I'm at, so right there, if I go that far around, I'm at 6 pi. The point of that is that 6 pi is going to have the same terminal side or the same ending place as the 2 pi angle did. So if they end at the same place, they use the same values for their trig functions. So that's the key that you want to remember. When the angles end at the same place or have the same terminal side, then you will use the very same coordinates you would have used for the one in the 0 to 2 pi circle. So in other words, the coordinates here are 1, 0. So for anything connected with the tangent of 6 pi, the tangent of 6 pi is going to be the same as the tangent of 2 pi. That's kind of how we're going to figure it out there. But we've got to figure out what that is. Tangent, remember, was y over x. So that's going to be what? 0. Okay, 0. Let's not do tangent. Let's do sine of negative 3 pi. Let's go with a negative angle. We haven't seen a negative angle today. Negative 3 pi. Where's that going to be?
Is that negative 30 degrees?
It's not negative 30 degrees. No. Let's try to think in radians with it, okay? Where's negative 1 pi? Remember, if you go negative, you go in that clockwise direction. So there would be negative pi. Here's negative 2 pi. If I come on around, there would be negative 3 pi. So we had negative pi, negative 2 pi, negative 3 pi. Negative 3 pi is going to be located at the same place as negative pi, which is technically located at the same place as pi, as far as our trig functions are concerned. Okay, we're using those same values. We wrap it around, and then we use it based on what we already know about that point. Oops. So the sine of negative 3 pi, the coordinates here are, what were the coordinates? Negative 1, 0. So the sine there is 0. Correct. Sometimes they'll give you a fractional looking angle. We have some of those. Maybe 11 pi halves. Let's see where 11 pi halves. What values will it use? The same ones associated with which angle? That's what we want to know. So if we're working with an angle that's 11 pi halves, we want to know what are we really working with there. There's 0, round to 2 pi. Okay, so it was 0, pi halves, pi, 3 halves pi, back up to 2 pi. 11 halves, you want to think about what that's equal to. What's 11 halves equal to?
5.5.
5.5, right. We don't write the angles like this. We don't write 5.5 pi, but for our thought processes, it's helpful to see that. 5 1/2 pi. So where will 5 1/2 pi be? That'll be the same place as what on this original unit circle? Same as 3 pi over 2. That's right. So what we have here is we go around, here's 2 pi. Again, it's 4 pi. To here is 5 pi. And then I need to go 1/2 pi. So that would be right to there. So this is the same as where our 3 pi over 2 is the same place that our 11 pi over 2 is located. When we wrap it around. See, I'm wrapping around that circle up there. So we're counting. So odd pi values will be over here at this side, pi, 3 pi, 5 pi, so on. Even pi values over here. And then any fractional parts we add in will fall in between those values somewhere. So to get any values for 11 pi halves, we're still going to use these coordinates, 0, negative 1. That's what we'll use. This is actually a long section. There's a lot of stuff in this section, a lot of material, I think. So it's a lot to think about. They also talk in this section about using your calculator to get the trig function values. We will come back to that when we're actually using the calculator to get those. Okay, so we will come back to that part. We won't totally leave it out there. So I want you to know how to do those. Most of you already have some idea, but there's a few things we'll need to look at on the calculator eventually. So now, with that in mind, what we've looked at so far, what other questions do you have off the ones you were looking at for today from this section? Go ahead. Oh, you were not raising your hand. Okay, that's fine. I thought you were raising your hand. Yes, back here.
Number 37.
Number 37. Okay, so let's look at it. Cosecant 45 degrees. Tangent 60 degrees. And I don't have my unit circle printed off for you to look at up here, but I like to draw a little diagram so I can see what we're looking at here. Try to help you see what we're looking at here. So there's my 45 degree angle. Well, kind of there. It's my 60 degree angle. The coordinates on the 60 degree angle are what? One half square root of 3 over 2. So look here how we're going on this to help you think about this a little better. Trying to help you think here. We just go over about to there and then come up. We're going over the shorter distance and going up the longer distance when we're at the 60 degree angle, right? You know there's the 60 degree angle and the 30 degree angle that they're flip-flopped. The x and y's are reversed. So think about how far out and how far up you're going. You're going almost all the way up to where that 1 point was there, right? Where 1 was. Square root of 3 over 2 is very close to square root of 4 over 2. Square root of 4 over 2 is equal to 1 because it's 2 over 2. So it's equal to 1. So we're only going over a little ways and then up further. As opposed to you would go out further for that 30 degree angle and then up just a little bit to get to that point on the circle. Now what about the 45 degree angle? What are those coordinates? Everybody's got those down, right? The 45 degree one? All right, so square root of 2 over 2, square root of 2 over 2. All right, so to get the cosecant of 45 degrees, we need to be thinking about which of the original 3 trig functions that we looked at. The cosecant is the reciprocal of the sine. So let's note that the sine of 45 degrees is square root of 2 over 2. It's the y coordinate. So now we know the cosecant of 45 degrees is 2 over the square root of 2. Or if we rationalize that, we get what? Yeah, square root of 2. So that's what we're getting for the first part. So we got square root of 2. And what does that mean when they're written together like that? Cosecant 45 degrees, tangent 60 degrees. We're going to multiply here. So we've got that, and then we're going to multiply by that tangent of 60 degrees. So we note that the tangent of 60 degrees will be y over x. So that's going to be square root of 3 over 2 over 1/2. And what's that actually equal to? Square root of 3, because we see those 2's go away. Square root of 3. So we have down here where we're working the actual problem, cosecant 45 degrees, tangent 60 degrees. All this stuff that I've written up in the middle there is figuring it out, working through to see what we get. Some of you don't like to show your work. This is a good place I advise to show some work. Okay. I have a son in 9th grade. He hates to show work. His teacher always says, you have to show your work. He does not want to show work. I think he's trying to save paper or something. I don't know what he's doing. So I'll say, why aren't you showing your work? He doesn't want to do it. I can't make him. Okay, what's square root of 2 times square root of 3? Square root of 6, good. Because when we multiply radicals, we recall, when we multiply radicals, as long as they are the same index, that means we're taking the same root, then we keep that root and we multiply the values that are underneath the radical symbols. Okay, so square root of 2 times square root of 3 will be square root of 6. Okay, I think you all have some better tools maybe to work through these and work on these a little more, but I'm going to give you a little bit more to think about here, okay, to start thinking about, still in this same section. But what if it's not a unit circle? We're still going to use those same ratios, x over r, y over x, those things, but we may not be in a unit circle always. So we have some problems in this section that I'm going to have you look at where you're going to be given a point on the terminal side of the angle. Kind of spread out the word standard. I don't know why, because I was looking over here, I guess. Okay, so if we have a point on the terminal side of an angle theta in standard position, here's what we're saying then. We've got some circle we can draw through this point where this is the terminal side. You know, here's our initial side. Here's the terminal side of some angle theta. We have some point here that's hooking up on that circle that's drawn around through where that angle is going through that point that they're giving us. The deal is, though, the radius might not be equal to 1. Okay, it all depends on where that point is that it's going through. So here's what we'll need to do. We'll need to be able to find what the radius is. If we know the x and y values, if we know x and we know y, which we would know if they're giving us that point up there, then we can find r. Because x squared plus y squared is equal to r squared always. X squared plus y squared will equal r squared, and that will give us our radius value. Why do we need that radius value? Well, when we go in and to find the cosine, we'll have to use the x coordinate over that radius. Okay, I'm going to lose my voice here this morning. The x coordinate over the radius. Must be fall allergies starting out here. We're experiencing fall allergies. All right, so let's do one here just to see what we've got. I'm going to give you a point here. This is number 78 off of page 376 I'm using as an example. Given 5, negative 12 is a point on the terminal side of theta. In standard position means, so we've got the vertex down here at the origin. Right, there's our vertex. 5, negative 12, where's that point? Yeah, it's in the 4th quadrant. Over to 5, down to negative 12, there's the point. So that's the point that the terminal side of my angle is hooking up with there. That means that the circle, that if I drew a circle that went around and included that blue segment I put in there as its radius, and my circle's going to go something like this. Okay, just to visualize what we have there. I'm interested, though, in the trig function values for this angle theta. So what I'm looking at here, I'm going to put my angle theta right here because I want to be able to look at the triangle that's formed using the x-axis and that radius value, the x-axis and that terminal side of the angle. So we're going to connect a perpendicular line up to here so that I can figure out what the radius is. We already know that x equals what? 5, right, 5. And y equals?
Negative 12.
Negative 12. Okay, and we're in the fourth quadrant. We know that. So the signs here are going to affect the signs of our trig functions. Now when I'm saying the signs, I'm talking SIGNs, okay? The SIGNs are going to affect, our trig function values, including the SIN sign, right? Okay, so let's look and see what the radius here is going to be. We have x squared plus y squared equals r squared. Before I can find the trig function values, I'm going to have to know what that radius value is. So x is 5 squared plus negative 12 squared equals r squared. That would be 25 plus 144 equals r squared. 169 is r squared. And the square root of 169 is 13. Now, some of you may have already known it was going to be 13. Maybe some of you are familiar with the Pythagorean triples. There's a few common right triangles that we will see quite often throughout this class. One of them is a 5, 12, 13 right triangle. Are some of you familiar with those? 5, 12, 13. If you have the legs of a right triangle being 5 and 12, even though one of these is negative 12, but in general, 5, 12, then the radius must be 13. What's another common Pythagorean triple that somebody knows? Does anybody know another one? 3, 4, 5 is another common one because 3 squared plus 4 squared equals 5 squared. And also 6, 8, 10. So some common Pythagorean triples I'll put over here. And you'll be seeing these throughout, but they're helpful ones to kind of keep in mind. 3, 4, 5. 6, 8, 10, 5, 12, 13. Those are common ones that we see quite often in this class. Okay. They're Pythagorean triples because 3 squared plus 4 squared equals 5 squared. 6 squared plus 8 squared equals 10 squared. If you don't believe it, work it out. Okay. 5 squared plus 12 squared equals 13 squared. So those are some common ones that we have. Well, now that we have that radius value, though, over there on our picture we were looking at, the radius we know is 13. So when we go back over there to that picture, we could find the trig functions now because we know that the cosine of the angle theta is going to be x over r. So what's x and what's r?
5 over 13.
Right, 5 over 13. Okay, the good thing is on this one we don't have any square roots on this particular problem here, so maybe that's a good thing. The sine of theta will be y over r, and that will be negative 12 13ths. Tangent will still be y over x. I'm using those same ratios that we used before. So the tangent will be y over x. What's that? Negative 12 over 5. Good. Cotangent will be the reciprocal of the, which one? Tangent. Reciprocal of the tangent will be?
5 over, or negative 5 over 12.
Yeah, so just negative 5/12, right? And then the secant will be the reciprocal of the cosine, 13 over 5. And the cosecant will be the reciprocal of the sine.
Negative 13 over 12.
Yeah, negative 13/12, right? So we're just kind of practicing using our ratios today for the trig function values. That's what we're looking at here more than anything. And then we'll be putting in some more properties with those trig functions as we go along. So I'm going to add a little bit to your assignment here. Some things I want you to practice with for next time. Does anybody have any questions about what we're doing here? Okay, let me add something to it. Where did I have you go to last time? On section 6.2.
13 odds, 31 to 37.
Okay, we did 13 through what?
19.
13 through 19? Is that all?
Yeah. And then we did 31.
Okay, I thought we did 31 to 37. Okay. So this was from last time right here. So if you didn't get that, go back and retry that. And then I'm adding to that. Here's what I'm adding today. Numbers 21 to 29 odd. And numbers 39 to 63 odd. And again, practice here. These are going to give you, you're going to be given 6 trig function values. And then this last part where the radius is not equal to 1, see what you can do with 77. We'll just do 77, 79, and 81 on that, okay, for now. See what you can do with those. So we're adding a little bit here to what we're working with in this section, trying to make sure we got a good understanding of those trig function ratios. And also we're getting that unit circle in our head right now, right? Maybe print it out, use a copy while you're working on this. Then, if you get this stuff done, print out that blank copy and see if you can fill it in without looking at the other one. Yeah? You could do that, right? Any questions? Okay, are we getting signed up on the My Math Lab? I had put in for it to open, but I don't think it got opened up, so I'll look back at that and see what's going on with it, okay? But for now, just worry about this for now, okay? I'll see you all back on Thursday. Thank you.